Okay. Uh, Good evening, everyone. Welcome to week 8 of Probability for Computer Science problem solving session. My name is Bhabya. Okay. I'm a PhD at IIT Madras, and this will be the final uh, problem solving session for this course. Okay. So there will be no, take note that there will be no extra session for this course. Uh, and let's begin outright. So last time what we saw was, so week 7, what we saw were things like independence. What did we do? We did Markov chains. Okay, that's just, oh, probabilistic method. Yes. Okay. This is what we did last week. Okay. Okay. And this time we are going to do um, set families was one of the topics, but the when I looked, the questions were either too trivial or too hard, so I didn't give anything from there. But please look at the lectures properly. Okay. And the other was um, this time is just superconcentrators. Okay. And streaming algorithms. Okay. Is there something that I missed? I don't think so. Okay. So these are week 8's content. Okay. So I've just made two questions. Okay. Because these are very specific topics. Streaming algorithm, the question has several parts. Okay. But the superconcentrator is a very specific topic. And designing questions is not exactly easy without making it too non-trivial. But I have one question in superconcentrator and one compound question in streaming algorithm. Okay, we'll look at them one by one. Okay, and this week is sort of like the application of probability. Although we saw a lot of applications already. Okay, and it's not about building any base right now. It's not about doing Chernoff bounds or techniques. Rather, it's about applying them. Okay. So let's look at this first question. I'll just take a screenshot. Okay. Actually, let me take a fresh page. Okay. So here's the question. Um, a directed graph G, V are the vertices and E are the edges, has n designated input nodes and n designated output nodes. Okay. So V, okay, the graph has categorized its node into n input nodes and n output nodes. Okay. And it is called a superconcentrator if for every k in 1 to n and every pair of set s and t with s equals t is equal to k. So if you choose two sets of the same size, okay, k can be of any size from 1 to n, there exists k vertex disjoint paths connecting the nodes in s to the nodes in t. Okay, for example, um, say something like this. Um, Okay, I'm not totally sure whether this will be a superconcentrator or not, but let's see. Okay, so let's say this is the graph. Okay, and this is set I, which is the input nodes, and this is set O, which is the output nodes. Okay, let me call it I1, I2, I3, and let me name it V only. So this is V1, V2, V3, this is V4, V5, V6. Okay, now suppose I take the set. Um, okay, let me take K equals 2. Okay, K equals 2. Then if I take any two element set, okay, V1, V2, okay, and any two element set from the output, okay, so this is S, and this is any two element set from the output V4, V5, okay, then I can come up with two paths, okay, V2, okay, I can come up with, so which one are the set? V1, V2, and V4, V5, okay, then I can come up with two paths which are vertex disjoint. They don't share any vertex with each other. One path can be this one, and one path can be this one. Right? These two paths don't share any vertex. Let's say I take k equals 3, and then s equals all v1, v2, v3. Right? Then v1, v2, v3, v4, v5, v6. So this entire thing is your set S, right? And let's replicate the same thing. And
but then what is there in the middle, in between S and T? You created few more nodes.
Yeah,
So
this is a
what?
fixed graph. This is a fixed graph.
But then it's okay that this is a fixed graph. But then apart from V1, V2, V3, and V4, V5, V6, I see few more vertices in between, right? As a middle vertices in between the vertices which are there.
Exactly. So that's the point. Your superconcentrator need not be bipartite. Okay. So the idea is that I have a graph. Okay, because I think two people have joined just now, Rajneesh and Harsh. I'll just repeat the definition. Okay. Uh, so we are looking at the definition of superconcentrator. Okay, although this is done in the lectures, I'm doing it once again. The definition part. Okay. Directed graph VE. Okay, V vertices, E edges has n designated input nodes, n designated output nodes. Okay, it is called a superconcentrator if for every k and every pair of sets S and T of equal size, that is k size, there exists k vertex disjoint paths, which means the paths don't share any vertices. So yeah, Goel. So let's say there are some vertices, right? So these are your vertices: V1, V2, V3, V4, V5, V6, V7. Right? There are vertices, and there could be edges also. Anyhow. Oh, by the way, yeah, Goel. By the way, sorry. Um. Oh yeah, yeah. Okay, that's fine. That's fine. No, nothing. um. Right. Your graph can look like this. Now, this is your graph, G, V, and it has two sets of vertices. One is the inputs and the outputs. Right. So there are n inputs. For example, let's say these three are the inputs and these three are the outputs. Input vertices, output vertices. That's all. I mean, that's what a super concentrator. I mean, that's the setup. Okay, there is this edge disjoint, vertex disjoint paths also. That's fine, but there could be vertices that are not neither input nodes nor output nodes. Is that clear, Goel?
So can we have outgoing edges from the output vertices and
Yes,
the incoming edges towards this?
yes, you can have. Okay, so that's a good point. So you could have, let's say, an edge going like this. Okay, but what you're not allowed to have is a cycle. Okay, is a there is it's not written. It needs to be a DAG, acyclic. Okay, cycles are not allowed. By the way, is that clear?
Hmm. Yes, yes, yes.
Okay, so okay, Showan has also joined. So a super concentrator is just a graph. Okay, Showan, it has two sets of vertices, an input set and output set, both of length same. In this case, n. Okay, such that any equal sized subsets you take of vertices in the input and the output, the number of there is at least k many edge disjoint path where k is the size of the subset you take. For example, if you take k is 2 and you take any two element subset of the input, two element subset of the output. For example, v1 v2 is the two element subset in the input, and v4 v5 is a two element subset in the output, right? Then you can see that there is this path from v1 to v4 and this path from v2 to v5. Clear? And let's say key is 3, which means you need a 3 element subset of the input and 3 element subset of the output. For example, this in this case, like the already input and output are 3 size, so therefore you need to take this entire thing and entire thing here. So what would be the edge vertex disjoint paths? Vertex disjoint, by the way, means that these paths are, it's okay if you share vertices. Oh, sorry. Uh, it's not okay even if you share vertices. Okay. Uh, you're not supposed to share even vertices. It's a very strict condition. Okay. So here is one way to go. Here is another way to go, and here is another. Okay. So k is 3. So I found 3 vertex disjoint paths. Okay. I hope the definition is clear. Is it clear, Ankita? Okay. Shovan, Rajnish, is this clear? Well, it's clear, no?
Yes, sir.
Okay, good. Okay. Yeah, Shovan is fine, no?
Sir, can
Yeah.
you just go through the initial part because I joined late? Just explain the initial part shortly, please.
Yes, no problem. Okay. What you have is a DAG. Okay. When is this DAG called a super concentrator? Okay, DAG means it's directed and it does not have cycles. Okay. It's called a super concentrator. Okay. Um, and by the way, the DAG also has some n number of nodes which are called input nodes and n number of nodes which are called output nodes. Okay, so your DAG could look like this, and let's say these three vertices are your input nodes and these three vertices are your output nodes. Okay, or this three vertices are your input nodes, these three vertices are output nodes. There could be nodes in the middle which are neither input nor output nodes. Okay, that could as well be there, right? Now, when is this graph called a superconcentrator? It is called a superconcentrator if no matter what size sets you take, equal sets you take, subsets you take from the input and from the output. For example, let's say k is 1. Okay, then you could, which means you take one vertex from the input, one vertex from the output. Or let's say k is 2. You take two vertices from the input and two vertices from the output. Okay, and k is 3, which means 3 equivalently 3 vertices from the input and 3 vertices from the output.
Any
Okay,
three or specified three?
any 3, but in this case, like the input set and the output set itself is of size 3, so you need to take the entire set, right?
Oh, yes.
Yeah.
But is this confirmed that we can have edges from the outgoing to the incoming without
Yes.
forming a cycle?
Yes. Why not?
Oh, all right.
Here, right? So for example, you have this kind of condition, no? It's going from outgoing to incoming, but it does not form a cycle,
Right, right. Yes.
right? Okay, good. Then um, if you take any k-sized subset, okay, any k-sized subsets, pair of subsets from input and from output, there is k many disjoint paths, vertex disjoint, which means like they are not even allowed to share vertices. That's strict. Okay. For example, you take k is 2, then you have v1, v2 as the first subset, and v4, v5 is as the second subset. Okay. And so, yeah. So this is your first subset, and this is your second subset. This is one path, and this is the other path. Notice that they are vertex disjoint. They don't share any vertices. If you had taken, for example, this v2, v3, and say v4, v5, okay, so this is not an example of a. So in that case, let me add another edge. Okay, in that case, let me add another edge. For example, v2, v3, v4, v5, v2 to v5. That's the path, and let's say there is an edge from v3 to v4 also. Okay, now this makes it a superconcentrator. Okay, this is just an illustrative example. Okay, it need not be an actual superconcentrator. I'm just giving you the idea. So if you take, let's say, v2, v3, and v4, v5, then you have an edge from, you have a path from v2 to v5, and you have a path from v3 to v4. That clear? Okay.
But there is no path from V3 to V4 now.
There is a path, right? That's what I changed just now. No, see, this is the path, and this is the other path. If I take, okay, there are not enough colors. If I take this as my, these two are my subset. Okay, right, Shovan?
Okay, sir.
Okay, so but I mean, of course, if you go through other subsets, maybe this is just something I came up with the top of my head, so it need not be correct. Okay, but it's just an illustrative example of what a super concentrator should do. It does not matter what k value you take. Okay, I hope the definition is clear now, right? So now that we know what a super concentrator is, here's a simple question. Okay, show that there exists a super concentrator with number of vertices is 2n and number of edges is n square. Okay, so number of vertices is 2n and number of edges is n square. Okay, hey, to show is that there exists a super concentrator G such that GV with input nodes I, output nodes O, where size of I is size of O, is equal to n, right? Such that number of vertices is 2n and number of edges is n square. Can you come up with a simple superconcentrator.
So, like in the source, we have n number of the vertices, and in the target, we have another
That's
n
right.
number of the vertices. And then let us go for bipartite, complete bipartite kind of the mapping from one vertex of the source to the one vertex of the target. Yeah, so this will act as super concentrator, and even with having the lesser number of the vertices, the total n number of the vertices. So what is the flaw here?
So yeah, okay. So basically we maximize the amount of each input node individual such that all input nodes interact with each output node provided a number of input branches are equal to the output branch. So basically we maximize the amount of each input nodes individual branches such that all input nodes interact with each output node provided number of input nodes. Yes. I think yeah, that's right, Harsh. Yeah, I think you and Goel are saying the same thing, right? So Goel, what you are saying is make a bipartite graph, right? And so right, and this is the input set and this is the output set. Note that in this case you don't have vertices in between, okay, because as soon as I put a vertex there are more than 2n many vertices. So I've already specified that there are the size of the graph is 2n. Okay, now what Goel is saying is make a complete bipartite graph, right, Goel?
Yes.
Make a complete bipartite graph.
Not complete. So instead of making complete,
Huh. Sort of making complete.
yes. Let us make complete here. That is also fine. Having n square number of the vertices,
Okay,
correct?
so if you make a complete bipartite graph, okay, complete bipartite graph. So what is it also called? It's called a KNN, no? N nodes in the
Yes,
left, N
yes.
node in the right, and K stands for complete. If you do that, then um, why is it a superconcentrator?
So, like, if I pick any vertex here, like say if I pick two vertices here, then I would be having two paths, and which would be vertex disjoint.
Okay, what are the paths here?
So, like, since you have not labeled here, like, say I pick two vertices v1 and v2. So then from v1 to vn plus 1, and then from v2 to say vn plus 2, these are the two paths and which are vertex disjoint.
Yes. Okay. Right. So let me repeat that. Okay, for everyone. I think this is what you were mentioning, Harsh, right? Okay, this is a KNN. The claim is that KNN is a super concentrator. Okay, KNN is a super concentrator, which means no matter what size subset I take from the first set to the second set, there are k many edge disjoint paths. That is, okay, for any k I take from 1 to n, okay, and for all s and contained in I and t contained in O, okay, um, number of edge, oh, not edge disjoint, vertex disjoint, text disjoint paths from vertices in S to T is exactly equal to K. Okay. Now why? Because see, observe the following. Okay. Now, like Goel said, if my K is 2, suppose K is 2. Okay. Suppose k is 2. So I take v1 and v2 as my set S, and I take say vn plus 2 and vn plus 3 as my set T, right? What we are saying is there definitely exists two paths that don't intersect with each other, which is trivially true, right? Because I can take a path which is going from v1 to vn plus 2, and since this is a complete bipartite graph, there is an edge between every vertex in the left to every vertex in the right. So there is definitely an edge from v2 to vn plus 3. So this is an edge disjoint path, a vertex disjoint path. They are not sharing any vertices. But now I can apply the same thing for k equals 3 also, no? And k equals 4 and so on. So this is the idea that since G is complete bipartite, okay, for any u in the left side and v in the right side, okay, there definitely exists an edge, which is itself a path of length 1. Okay, so for any s equals v1 v okay, that may not, okay, this is a bad naming convention. Okay, for any, take any two set in s and t. So for any u in s and v in t, okay, what I can do is I definitely have this as edge, and this is a vertex disjoint path of length 1, right? Vertex disjoint path of length 1. Now, and we are done basically, because you can always choose in the following sense that um what you do is you order these edges, let's say without loss of generality. Okay, S is v1 v2 vs, and T is say vs plus 1 vs plus 2 and so on till vt, right? I'll just do one thing. I'll take my paths as v1 to vs plus 1. This is the first edge. v2 vs plus 2. This is the second edge, and so on. Same thing we did earlier. Vs vt are disjoint paths, vertex disjoint. Okay, and this is basically what we are doing, right? Where both are key length, no? So what I can do is this is key. Okay, let's just not confuse. But is that clear? It's the, yeah, it's the most naive algorithm to achieve this. Okay, good. Others, is it clear? Shovan, Ankita, Rajneesh. Okay, good. Clear, no? Okay. Shovan, Ashwini. Okay. 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 So now this was the simplest algorithm to achieve this, right? Now, what is the problem with this? I mean, the problem with this, I mean, would be that there are just too many edges, no? I mean, there are n square edges. That is the largest number of edges that can happen in a bipartite graph. Right? It would be natural to ask a question that can we do it more efficiently? Can we bring down the number of edges? Can we bring down the number of edges? Okay. So, or rather, can we bring it to linear size? Now, that is what we are going to show using probabilistic method, that there exists a superconcentrator. Okay. And another thing is, let's do part C first. Okay. Can you think of an application of superconcentrators so that we are motivated enough to do part B? Okay. Can you think of some context in which this could be helpful?
So like say from the set S, people are making calls to the people which are there in the set T, and they should be able to make call individually. I mean, the persons from S should be able to make a call to the someone from T individually, and there should not be any overlap kind of the thing.
There should not be
So
any
it's
overlap.
overlapping kind of the thing. So how many different connections are required in between S and T, so that each one from S can talk to yeah. I mean, people from S, from the set S, can talk to the people from T individually.
Individually. Yeah, I think that word can be improved slightly. Okay.
Okay. Okay. So like say it's like S is a set of the resources, and T is a set of the consumers,
Okay.
and so S is a sender, and say T is the receiver kind of the thing, and
Yes.
then sender should be able to. There should not be any overlapping kind of the thing. I mean,
Huh.
yeah.
Okay. Okay. Any other applications?
So I can think of an application there are so many war going on. In that type of situation, one supreme leader want to give any news to his commander,
Okay.
to his army chief or commander,
Huh.
but they should send it so much efficiently and so much securely that no one can interpret that what message is going from one side to another side. So in that case, they want a secure path without internet or without something. In that cases, they can use every time they can use any disjoint path where there will be no overlapping and no one can breach that route to get that news. So in that cases, we can use this type of algorithm.
Okay. Okay. I think
Maybe
it's
maybe
close
I
to
can
what.
be wrong. It's just my idea.
Okay. 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 Good. Good. So yeah, I think it's close to what Goel is saying. So what you mean is like, um, when you send messages, um, so since it is, this does not occur, at least I mean, these paths, there is a way to avoid these kind of overlaps, right? There is a way to avoid overlaps. Okay. So there is a way to avoid overlaps. Your messages will not get garbled up, no? Because I mean, two messages are reaching the same point, and if you think of these as like data packets, then they will not overlap, right? And they'll be safely transmitted to the destination. I think there is a nice word for this in computer networks, no? When two data packets reach the same point and then they get corrupted.
Multiplexing or no,
Multiplexing is it's a way
something
to
else.
avoid that. But what is the
Yeah.
error called? What is the issue called? I mean, I mean, this is out of syllabus for this course, so I understand if, but
Uh, issue of collision of the
Yes,
packets.
yes, yes, yes. Collision. Oh, super concentrators are in the syllabus. I mean the collision part. Okay. Yes, collisions. So it helps in avoiding collisions in. Um, could you do C again? I disconnected internet. Oh yeah, yeah, Harsh. I've not said the final point yet, so you can still think of an application for super concentrators. Okay, so super concentrators. Actually, you understood the definition at least, right, Harsh? So what would be an application of super concentrator? Well, like as Shovan and Goel said, you avoid collision. So as a consequence of that, what can you achieve in network communication? Okay, so what advantage in communication? So since there is a way to avoid collisions, okay, what advantage can you achieve? So you can still think of that. Okay, you can still think of that. Let's do B. Keep that question at the back of your mind, and we'll come back to this. But I hope that there is a good motivation to study this. There are theoretical applications also. Okay, but here, practical applications also it's used a lot. Okay, so now since we came up with a very dense super concentrator n square, it is as bad as it can be. Okay, but what it tells is that these graphs do exist. Okay, it's not you know impossible to think of this graph. It's not some object that we don't know exists or not. It's just not a dream object. It does exist. What you want to say is, can you come up with a better super concentrator? But now I want you to use randomness. I want you to use the probabilistic method. Okay, so how efficient? Oh, it's very efficient. I mean, number of edges is order n, and of course you need minimum order n edges, no? Uh, so because every vertex you are talking about across all subsets, no? From S, any S and any T. So it means that from every vertex there should be at least one edge to any of the person in the other group. Okay, every vertex in the input there should at least be one edge. Okay, so this is like very efficient, right? You can say that you can say with certainness that these super concentrators, efficient super concentrators, exist using the probabilistic method. Now remember, the probabilistic method does not um, give you an explicit construction. It tells you the existence of objects. We did it in the previous case. This might be slightly technical, but since we did the probabilistic method last time, so I expect like you guys will catch up. Okay. So, but no problem. I'll do it step by step. Okay. Let's do question B now. Okay. What do you need to show? There exist super concentrators. Oh, and this A was there as an exercise, no, in the lectures. Okay. So this exercise we did it. In the lectures, we also show some 3i, 3j, 6k kind of super concentrator, right? But this time we'll talk about a general super concentrator. Okay, there exists a super concentrator. Okay, um, with order n edges. Okay, great. So, um, should I? Should I? Okay, great. So here's an idea. Okay, what you do is here's an idea how to build the graph. Okay, so how do you build the graph? You make 2n edges on both the sides. Okay, this is, of course, this follows v1, v2, and so on till vn. Or let me name them differently. Okay, let's name it u1 to u1, u2, so on till un, and v1, v2 till vn. This is input, this is output. Again, we'll make a bipartite graph. Okay, start with I equals u1 to un and o equals v1 to vn. So total there are 2n vertices, right? Now fix a d. So this is the degree of each vertex. Okay, now here's the idea. What you do is you uniformly randomly choose d many vertices as neighbors.
Could you share the question again, please? B part.
Yes.
Thank you.
Can you show that there exists superconcentrators with linear number of edges using the probabilistic method?
But in part B, what is the number of the vertices?
Number of vertices is still 2n because that is there in the definition itself. Oh, yeah, you just assume it to be 2n.
Okay.
Yes, you can scroll down. Thank you.
Okay. 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 Right. Now again, we'll come up with a bipartite graph only. Okay, to make things simple. So you fix a d. Okay.
Bol. I'm sorry.
Yeah, no problem. You fix a d where d is the number of so d is the degree of each vertex. Now what I do is I uniformly randomly, okay, for every ui in I, okay, choose d vertices from O, set O, uniformly at random. Okay. And that's what you have, right? So there are d many vertices. For example, un could be attached to v2, let's say, and so on till vn. So d many, right? So what is the total number of edges in the graph?
So since every vertex is connected to d other vertices, so there would be dn number of the edges.
That's right, dn. So far it's linear if d is a constant. So assume d is constant. Okay, some 100,000, whatever. Okay. Now this is capital O. Okay. Assume d is constant, so it's linear. Okay. Now that's it. Now what I say is, with good probability this is going to be a superconcentrator. With non-zero probability it's going to be a superconcentrator. Okay. And if you say that the probability that this is a superconcentrator is non-zero, okay, it means that there is at least one superconcentrator with this property, right? That's why it's contributing to a non-zero probability. Otherwise the probability would be a 0. So we are simply reapplying the probabilistic method we saw last week, the week before last week, right? So that's our claim. Okay. Now claim is, okay, that this G is a superconcentrator. Okay, so what does it mean that it is a superconcentrator? That is, for every S in the input set, the left hand side, okay, and S is equal to K, okay, the number of neighbors is at least K. Why does it help us? Because this is nothing but edges, no, the number of edges, which is nothing but length one path. So my claim is that if you take any subset, okay, let me copy this, or there is a duplicate, no? Okay, let's just copy this. If you take a subset S, and if you look at its, okay, let me increase the thickness, S, and if you look at its neighbor set NS, NS is large. If you do it randomly, okay, this is my claim. Now why does it help? Again, NS is nothing but the number of edges, right? If the number of edges are large, okay, then these are then these are edges, and therefore length one path. But what is this enough? Is this argument enough?
Seems to be enough because this is the bipartite graph, and so there is no chance of having the overlapping of the vertices in
But
somewhere in the middle.
but in a very bad case, they may overlap, no? Well,
So I mean, along with this, that the neighbors are greater than or equals to k, I need to ensure that one vertex of the S is getting mapped to the one vertex of T,
yes,
and there is no overlapping here.
yes. But yes, you are right. So but is everyone convinced that this would ensure that this is a super concentrator? Okay,
Yes, yes.
I'll give you a better argument also. Yeah, Rajnish.
No, no, continue. I got it.
Oh, okay. But who's to say that this is definitely going to be a super concentrator? No, maybe there, it's not a super concentrator. Maybe it may happen. Let's say that there are these vertices, and there are a lot of edges. There are a lot of edges, and but the neighbor set is shrinking. Neighbor set is shrinking. There are a lot of edges, but the neighbor set is shrinking. Can this happen? This cannot happen because of something called the Hall's theorem. I don't know whether all of you have seen Hall's theorem or not. Okay, but this is a very famous
Can you
theorem.
repeat your argument again in this? In this example, green bubbles. Can you repeat
Yeah.
that argument that you did again?
Yeah. What I mean, Harsh, is that is this enough to prove that this is a super concentrator, that there are k many edge disjoint path? Why should this be true? Because maybe I can come up with an example where I have my set S, and there are so many edges, okay, but this set is actually shrinking, okay, but okay, actually, now that I think of it, it does not even require Hall's theorem, right? Because the neighbor set itself is high. Edge disjointness, is it? Oh, okay. It's not that. Yeah,
So what you're basically so what
yeah,
you're
okay,
basically trying to okay. Now you continue, sir.
yeah, sorry. So what I mean to say is, okay, the size of the set will not shrink. It is at least k, right? You want to say that there is definitely an edge disjoint path. Okay, there is definitely a set of edge disjoint paths from S to T, right? Which is n of S exactly. Now, how can you guarantee that? I mean, this statement requires a proof, right? I mean, even though it looks like it should be true, it looks like it should be true. The guarantee is given by Hall's theorem actually. Hall's theorem says that it's a characterization of perfect matchings in bipartite graphs. So it means for any bipartite graph G, okay, if my if it holds that for all S, okay, in bipartite graph G, let's say LRE, okay, left half, right half, and edges, any subset of L, okay, let's say the neighbor of S is greater than the size of S, then G has a perfect matching. Not only this, the other way around also holds. This is the power of Hall's theorem. Okay, if and only if G has a perfect matching, then definitely if you go across all this is a very interesting theorem actually. If you go across all subsets, okay, and take any subset, the number of neighbors will always be larger than itself. And the other way around also holds that if the number of neighbors is large, then G definitely has a perfect matching. This is a litmus test for checking if there is a perfect matching in graphs. Okay, and here this is exactly that, because the size of S is also k, no? So Hall's theorem guarantees that there is a perfect matching. What does perfect matching mean? That that in that graph there is a unique way to it means that there is a set of edges, okay, there is a set of edges that don't intersect with each other and they cover all the n vertices. This is a perfect matching. But these are also what? These are edge disjoint paths. Right? So this is guaranteed by the Hall's theorem. So you can see it intuitively also that there are so many neighbors, then there should of course definitely be unique disjoint paths. But Hall's theorem is a way to prove it, that definitely there exists. Okay. Now that side is clear. Okay. Now that is that is what we claim. Okay. This claim is enough. So let me write it claim 1. Okay. Okay. Now we want to prove. So this is claim 1. Okay. But claim 1 always existing, that we don't expect. No. So what we want to say is, what is the probability of this event happening? So what is the probability? Oh, so claim 1 implies superconcentrator. Okay. But what is the probability of, okay, let's not write it as claim 1, let's look at it as situation 1, case 1 instead. Okay, the probability of case 1 happening. That is, what is the probability that neighbors is at least k? If you take any subset, okay, and if you take any subset from the left hand side, right, and the size of set is k, what is the probability of this happening? So you multiply the first probability of finding key nodes in the output bubble and multiply that with finding unique paths. Yeah, exactly, Harsh. So that is how you will calculate this probability, no? But that will be a difficult calculation, right? Right? Yes. Okay. So let's do the opposite. Okay. Let's do the opposite. Yeah, go ahead.
So like, what is the case one? What is the case one
Case
that
one
the size?
is the good case. Okay, case one is the good case. So it is that no matter what subset you choose using this construction, right? Using this random construction, no matter what subset you choose, the number of neighbors is greater than k. At least k.
Oh, I see.
Okay, this is a
So,
good case, right? Because this guarantees superconcentrator. Because you are doing it for every subset. I mean, you're guaranteeing it for every subset,
yes.
right? This is the good case. So you want to see the probability of this happening. If the probability comes to non-zero, then you know that it exists. I mean, there is a good case that definitely exists, and since the good case exists, I mean, such an efficient so super concentrator exists because if it why? Because it is contributing to that non-zero probability. You know, otherwise the probability would be zero.
Right. So this value, I guess, would be a dk and then divided by nck. Dk in the sense that, so what is the maximum possibility that each node is having a d number of the neighbors. So then k
No.
number of the nodes would be having a dk number of the neighbors.
But you need to that the I feel like the denominator is fine, but the numerator should contain all the events of good superconcentrator. No, you're talking about like one supercon. You're talking about the size of one superconcentrator, right? Go ahead.
Oh, yes. All
Yes,
right.
right.
So in how many different ways? I mean,
Yes, and that's a difficult calculation, no?
yes.
Right? Okay, now yeah, we are convinced. So, but to step back, this calculation, if it is greater than zero, if proved to be greater than zero, implies such a good case, that is graph, exists. Because if not, then the probability would be zero, no? Because no such case exists, right? So, but that is exactly what the question is asking, whether it exists or not. This is what we need to prove. This is our target now. Okay. So to do this, let's see. To do this, let's show the opposite. Okay. To do this, we shall prove the opposite. That probability that ns is less than k ns is less than k is less than 1. Okay. We'll use this. Okay. Is everyone convinced? If we prove that this is less than 1, strictly less than 1, then the complementary case means that it's strictly greater than 0. Otherwise, if it were equal to 1, it would mean that the complement case would be 1 minus 1, 0, right? So, proving that the complementary case is strictly less than 1 is equivalent to proving the original case is strictly greater than 0. Okay, great. So, what is the probability of this case happening? Okay. So, fix an S first. Fix a subset S for a fixed subset X. Okay, for a fixed subset X. Okay, S is no more variable. Okay, let's look at the probability. Okay, now this is what is called the union bound method. Okay, what is the probability um, that all the decay edges, because every S, okay, all decay edges land in a set of size less than k. So basically, you're looking at the bad event, no? When you fix the S and all the neighbors lie in a set which is less than, which is of size less than k, right? So what does the bad case look like? The bad case looks like this. So any S you take, okay, or there exists some S such that it shrinks down, the neighbor set shrinks down. Okay, this is n of S, and this is less than k. The size of n of S is less than k. It shrinks down. But in total, how many edges are there? There are dk any edges, no? So let's look at probability over any edge. Okay, this probability, it will be more confusing if I parameterize. What is the probability that all the dk edges land in a set of size less than k? So can you give me a count of this? All the edges are chosen independently, no? I mean in the construction. So all the edges are chosen independently, no? So, right? Set, let's say t. We'll fix t. Oh, no need to do that. No need to do that. This is bad. Okay. Right? So, I mean, all the edge choosing was independent, you know. So, what does it mean? Like, um, okay, what was the construction? Fix a D for all I choose D vertices from O uniformly at random, right? So I chose this uniformly at random and chose this uniformly at random and so on. So for any edge, okay, let's say you fix a vertex. So what is the probability that edge, let's say E5, any edge E5, okay, lands on or incident on, let's say V7? What is the probability?
That value is 1 by n.
1 by n, right? Because we are doing it uniformly at random. There are n many edges here, and we are uniformly at random, just allocating it randomly. And for every edge, it's 1 by n, right? Now let's look at this back. Now what I can do is I can break up this probability, right? Because each of these decay edges are independent. Independent probabilities multiply, right? So probability uh, that say edge E1, okay, falls in size set. Oh, okay, I need to do this. I need to fix the set, is it? Yes, set T size. Okay, falls in T, probability edge E2 falls in T, and so on. Probability E dk falls in T. Okay, and T is of size less than k. right? Okay, this is at most, since the size of t is less than k, this is at most k choices out of n choices. No, k choices out of n choices, k choices out of n choices, and so on, which is equal to kn to the dk, because there are dk many. Right? Okay, so far so good. Now, but I want a probability over S. No, we've already fixed S. Now let's now we use something called the union bound. Okay. Okay, we've seen it in the course before, but union bound is a simple thing. Okay, it just sounds, if you have events A1, A2, and so on till AN, probability of union across AI is happening. Event A happens or B A1 happens or A2 happens and so on, is upper bounded by n times k by sorry, what am I saying? N times, oh sorry, probability of AI, summation probability of AI. So it is at most the sum of probabilities. It even follows from inclusion exclusion. So the probability of event A happening, B happening, C happening. I do not understand the part where you showed it is strictly less than k by n raised to d. Okay, no problem. So Harsh, I hope this is clear. No, this is clear. Probability that you fix an edge, it lands on a particular vertex is 1 by n. This is clear. Now let me modify it. What is the probability that edge E5 lands on V5, V6, V7? So if E5 lands on V7 is 1 by n, then what is the probability that E5 lands on V6 or V7? Okay, this is or, okay, V6 or V7. Okay. So what is the answer? V7 is 1 by n because every vertex on the right is chosen with probability 1 by n. Okay. Yes. 2 by n. Why? Because V6, it can land on V6 with probability 1 by n or V7 with probability 1 by n. Harsh, this much is clear? Okay. 2 by n. Or the other way you can see it is there are two favorable outcomes and n is the total number of outcomes, then it's 2 by n. That's another way to see it. This way to see it is actually more helpful, okay, in the long run, because because this only the previous one only works when you think about uniform probability. Okay, but see, 1 by n for v6 and 1 by n for 2 for v7. Okay, now let me ask the question: what is the probability that edge e5 lands on v1 to vk? K by n. Yeah. So here you fix a set of size t, oops, and its size is at most n. So yeah, yeah, same logic. Yes, you get it now. Okay, good. And total there are dk many edges. Okay, which we already saw. So okay, so union bound simply says that the union of events is at most the sum of the probabilities. Okay, a1 happening or a2 happens or a3 happens and so on. Notice that I can look at the failure probability in terms of union bound. This is now a very, very useful technique. It's used all over the place. Okay, in randomized algorithm, union bound is very, very helpful. Okay, now, so what we do is we'll apply union bound. Okay, so it is helpful in the case where you look about failure probability. It is when at least one case fails. Okay, what is the probability when at least one choice of S fails? Right, when one choice of S fails. Why are we looking at least one choice? Because all S choice is not the bad case. Okay, because it's a lot of things are not getting covered. Maybe there is a graph where you look at almost all the choices, and it is the nk is coming greater than k, ns is coming greater than k for everything, but there was one guy for which nk was shrinking. This is bad, no, because this is not super concentrator according to the definition. Right, so the bad case is at least one choice of S fails. So this is nothing but what we are estimating. Okay, this and this are the same thing. These two are the same thing, by the way. Probability that given any S, ns is less than k, at least one. Okay, choice of S fails. Notice that at least one means it's a union of events. Probability that union over S choice S fails. Okay, what does choice S fails means? Union over S no, it's probability, sorry, the event that S is n of S is less than k. Right, it's the same thing. Now, at least one choice fails is either the first choice of S fails, or the second choice of S fails, or the third choice of S fails, and so on. Okay, now what is this? This is the union bound form. Applying union bound, it is at most how many choices of S are there, because that is the number of events. No, that is the number of events. S is of size k, so there can be at most, okay, or let me make it clear by number of choices of S, number of possible choices of S times probability that n of S is less than k for a fixed S, for a fixed S. Okay, for that S, which is at most, remember what did we calculate this to be? K by n to the dk, and number of choices of S, S is of size k, number of subsets of size k from n set of size n choose k. So this is the final bound we get. Okay, now is this bound so this is the probability bound. Okay, now notice that if I keep d as very high, d is 100, even 20, and so on, is fine. If d is 1000, you can do it as an exercise. Okay, I need to move on to the next question also, but d is like very, very large. D is like very large constant. Then n choose k, kn to the dk is definitely less than n. Okay, but what is this? At least one choice of S fields, but this is nothing but the probability we were computing, which is nothing but the probability that ns is less than k. This is nothing but probability that G is not superconcentrated. But if the case that it's not a superconcentrator is less than 1, the probability is less than 1, it means that probability that G is a superconcentrator is greater than 1. Okay, so therefore, which means that there exists a superconcentrator with number of H's is linear. And that is how you prove it. Well, it's not an easy question, okay, because there are a lot of ideas used. But what I wanted to demonstrate is all the tools we've gathered, okay, over the course, or the tools we've gathered over the course have been applied in this question, right? And they fit in perfectly together to actually show that these objects exist using the probabilistic method.
So I have two questions here.
Yes, well.
That this method only showed the existence of such a super.
Yes.
But then how to find that? How difficult is to find that possibility?
Yes. Yes. To do that, you need to analyze this. Okay. If it is very small, okay, try to simplify this. If this is very small, if this is very small, then yeah, then it means that there are more superconcentrators. When you randomly sample, you have a high probability of getting a superconcentrator, right? Well,
Yes.
yes. So now, so the technique would be to make this probability as small as possible. Achha, okay. Okay. To make this this probability as small as possible. So a good way to do a lot of, but although this is a search algorithm, so success amplification, I mean, doing it over and over again will not really help you. But I feel like this probability is yeah, this probability should be small. That's what I feel personally. Well, if this is small, then your work is almost done, because I mean, you can just randomly sample and get a superconcentrator with a very good probability. And if you get with a probability 99%, then I mean, it's very, very unlikely you're going to get a non-superconcentrator, right? Also, look at the analysis of this. Okay, at this point we've hidden some details, no, because we did you use the union bound, that is fine, but at this point we hid some details by k by n. It's not really k by n. This is not really accurate. If you come up with a finer analysis, you might get a better bound and then prove a better, this happens a lot in this algorithms research, by the way. Okay, you have a standard way to do it. The algorithm is very simple. People come up with better and better ways to analyze it and show that the same algorithm actually does a lot better than you expect, than they thought of before. Okay.
And yeah, and since this problem is modeled as the bipartite graph, so is this of the order of n? Can we do better than this of the order of n, and probably the sublinear viso? Because the graph is modeled as a bipartite, and wherein we miss the possibility wherein there could be intermediate vertices, and even with the lesser number of the order of n number of the vertices. and still we can get the super concentrator.
I don't really know an answer to that, as in I cannot give you an exact answer whether that exists or not. But my belief would be that this is like a very optimum as it gets. To assume that a sublinear number of edges still guarantees a super concentrator would be very surprising personally, because intuitively you would expect that from every edge there is at least one edge, no? That is what it means to be linear, right? To mean sublinear, it means that there are there are vertices from which there are no edges. There are isolated vertices, right? Well,
That would mean that, like, say, it's true that if the value of k becomes equals to n, then definitely we would be requiring, say, n number of the edges, and that is the minimum requirement. However, say if we keep the value of k in control, like say we are having we cannot cross the value of k, say, by n by 2, and in that case it's still like in this case we still require the number of the edges of the order of n and having the vertices at 2n. And if you fix that the value of k cannot cross, say, half of the n, then still do we require the edges of the order of n, or why so? Because my only apprehension here is that this entire thing has been modeled as a bipartite, and we did not exploit those possibilities wherein the middle vertices can also exist. And yeah,
right. Um, so if you allow the middle vertices to be present, can you come up with a better, right? That's what you mean, no? Well, hello? Well,
yes,
okay.
and moreover, if we parameterize this, the value of k, and maybe in terms of n, but then
Oh,
if
yeah.
k is equal to,
By the
yeah,
way,
if k,
here, even though it looks like this expression is huge, okay, when you actually simplify it, you realize that this expression is not that challenging. Okay, you want me to do that? This expression actually converges to a very small number. This
what
looks
is
like
this?
because for any k,
Okay, okay.
k can be as large as n by 2. Okay, and still k being n by 2 is the largest value that n choose k can achieve, no?
Yes,
Right? So let's see why that can be true. Okay, I'll try my best right now. Because this k by n
Or-
has a dk on top. Okay, so you know by there is something called Stirling's approximation.
yes. But that is very
There's
complicated formula. Yeah, 1 by uh, square root of 2 pi something, n
yes,
by,
so n by k to the power k ek or something, no?
yes.
Okay, I don't remember the exact form. Just give me 1 minute, okay? I need to charge my laptop.
Yeah, sure. Otherwise, you can skip this one because one more question is remaining, and
Oh
then
yeah.
I will try this thing on my own. And
Yeah,
yeah,
you can try this. Okay, but
sure.
this will converge. You I get your problem that this k might be causing a problem. No, k could be large, so you feel like this value could come to exponential.
Yeah.
Yeah, but no, this k being this will definitely converge. Okay, so okay, let's move on to the next question. Okay, others, is there any questions? Are there any questions? Oh, Kishore is here today. Hi, Kishore. Yeah. Shovan, Ankita.
Hello, Bhavya.
Yeah. Hi, Kishore.
Sorry,
Yeah.
I was a bit late
Oh,
joining.
that's fine. That's fine. I can't recover the first question, but the second question we'll look into it. Okay, Kishore. Okay. Yeah. Okay. Good. So we look at something called streaming algorithms. Okay, it's a hot topic nowadays. A lot of interesting results in this domain. Okay, what is a streaming algorithm? What is a streaming algorithm? Does anyone know? Okay, so the model is as follows. There is a stream. It's called a data stream. Okay, and A1, A2, and so on till AM, and they are coming one by one. Okay, and you can see them one by one, and this is called a pass. Okay, you go through them. Now the question is to compute something on it, over it. Issue is, I mean, you can of course say, okay, I look at the entire data and then I'll do a second pass. Whenever I just do any algorithm, okay, I can just compute any algorithm in this model. But what is the problem? Okay, the problem is, okay, for example, let me say, for example, check if some complicated stuff. Let's say check if okay, not something like multiplication. Okay, first let's do something else. Check if an element exists. So you can look at the first box and then the second box is to check element if 10 exists or not. You can look at the third box, and then finally when something like 10 comes, you can say, oh, okay, 10 exists. And when you, at the end of this entire stream, you can say yes. Okay. Or you don't see 10 anytime, then you'll say no. Okay. But let's say I ask you a more, oops, complicated question. Okay. That is, check if uh, okay, I don't know why I can't come up with a complicated question, but okay, we'll see. But oh, by the way, yes, part C. Can you think of an application for superconcentrators? Yes, I forgot to come back to this question. Um, we saw that there are we can avoid overlaps with it. So one immediately application about this fact is very efficient parallel communication. Part C is efficient parallel communication. Okay. So I think, Goel, that is what you meant by independently, right? The word I was looking for was parallel, because independently could mean,
Yes,
right?
yes.
So if any group of people need to communicate, you can make them communicate parallelly without worrying about collisions. Okay, so this is a very nice application. Okay. Coming back to this model, okay. Um, now what you want to, but what is the problem? Okay, is for example, I tell you like which element occurs most frequently. I ask you. Oh, you'll say you'll just go through the stream. No, oh, okay. A1, you'll keep a table. Okay, you'll keep a table. Okay, you'll keep a table for A1. You'll keep a table for, oh, okay, objects. Okay, yeah, okay. So you'll keep a table. Let's say A1, A2, A3, and then you'll see. Oh, so far A1 has occurred once. A2 has occurred 0 times. A3 has occurred twice, and so on. Every time you'll increment or decrement each time. Right? Now you'll maintain this table, and at the end you'll say, oh, okay, item A7 appeared 100 times. This occurs more frequently. But here's the catch: you have limited memory. How much memory does this require? This requires order n space. Right? I'm assuming each of the element takes constant space. Okay, order n space. Now, but you have limited memory, say something like order log n or constant space. Now it's almost magical if you can compute something like majority, right? Because you have so little memory that you can't keep track of which element, or let's say you decided to keep track of A1 element A1 occurring, but and A2 occurring, A3 occurring. Okay, three A1, A2, A3. But what about the rest of the elements, right? So how do you do it in so little space? Maybe element A100 occurred the most number of times, but you are only keeping track of A1, A2, A3. Now that is the catch. So by the way, the data stream is of length m, and each element takes from let's assume to be integer only. Each element ai to a. Okay, so you want takes a number. You can assume that these are numbers, list of numbers. So I hope the model is clear to you. Yeah, Kishore.
Yeah, see, basically the streaming algorithm, when we say, basically it is trying to identify the data, or we can say the element. Let us suppose we have sent a data stream of 100 bits, and then each bit it tries to identify.
Yes, if it is given in the form of bits, sure, but it could be like groups of bits also.
Yeah. So just taking for example, we sent in a bit form. So is it something based on the catch? What you are doing is the limited
Yes.
memory.
Yes.
So given these two, right? So is it the motto is to identify all the streams or the required stream within the provided data stream? I mean, provided data stream is 100 bits.
Yes. So you fixed some. So 100 bits is your complete stream, right?
Yeah, right.
So there are several models studied actually, but sure, 100 bits is your stream, right? And so what you want to say is, I allow you limited number of passes, maybe just one pass, or maybe two passes back and forth, or maybe three passes and so on. And you have very limited memory. You can't store all the elements in your list in your own memory. For example, like this is used in
Yeah, got it.
right?
Let me tell my understanding. See, of course, the reading of data is a number of times we can do, but picking and storing the values, for that we have constraint. Is that
Yes, storing values you have constraint.
for storing the values we have the limitation.
Limitation, yes.
But as per the streaming algorithm, the data can be read. The data stream, let us suppose the 100 bits, can be read n number of times, right?
Right, exactly. Good. So this is where the concept of passes comes. Right. You are allowed to move from left to right and right to left. I can even constrain the number of passes.
Okay.
Okay. Now,
Because even that to take the space, right? Even the passes also take some space, so we have limitation on that as well.
passes need not take space. That we are not taking into consideration.
Okay.
Okay, but the number of passes, I tell you, only do it in 2 pass or 1 pass. Okay.
So if passes doesn't have any relation to the what do you say, the space, why we are restricting it to 1 and 2 times? Why we are limiting it?
Because if you allow multiple passes, then you can compute a lot of things. For example, majority you can compute. Because first pass I will restrict it to, say, okay, so my numbers are between 1 to n. First pass I'll only count the number of ones. Second time I pass, I'll only count the number of twos. And I'll compare it with the number of ones that I stored in my memory. Third time I'll compare with 3, the number of threes. And this time number of threes is more than twos and ones. So I'll update. I'll put in my memory 3 occurs 142 times. And then fourth pass I do. Given n passes, I can compute majority easily. So now you see that number of giving me more number of passes is actually helping my cause, right? So I want to study in a constrained setup. That is, even the number of passes are restricted.
You see,
Okay, a good example of
just in case, let us suppose we have only 1 bit of space, and then based on the one pass we'll get one result. So probably we have to restrict the pass to only one time, because it results in a 1 bit output, and then that is the only output we can store within our space, available space.
If your space is only 1 bit, that's right.
Okay, got
but
it.
Maybe you have more bits also. Let's say you are allowed to store 100 bits, and so that is also fair.
It depends,
right?
based on
Depends. Right. Okay, good. So now I hope the model is clear to everyone, right? I'm sorry, your voice was inaudible. Oh no. Could you explain the logic of pass? So, Harsh, you can imagine this data stream to be a list of numbers. Passing means I look at these numbers from left to right. I can either store something in my memory or not. I can choose to ignore and move on. And when I reach from the left end to the right end, that is one pass. I can go from right to left also, that is another pass. I can do multiple passes, but as I increase the number of passes, I allow you more passes, things become easier to compute for you. For example, I can compute majority, which is like which element occurs most in this list. I can do the first pass and just look, since this is my domain, okay, this is called my domain. Okay, this is where the elements take numbers from. Okay, only these kind of elements exist, 1 to n. Now, at first I can just count the number of ones. I can store it. I'll say, okay, 1 occurs 31 number of times. Okay, and then the second pass, I'll count the number of twos. And I'll see that, 2 occurs only 12 times. So no need to remember this. And but I still remember 1 occurs 31 times because this is the most number of times it has occurred. Then I count the number of threes. I'll say, 3 occurs 142 number of times. This is what I'm storing in my memory. No? So since it is greater than the number of ones, my current maximum, I'll remove the current maximum from my memory. So at any point of time, I just need say around 4 log n, 4, okay, okay, 4, okay, for now, let me not confuse you with log n. 4 cells, right? 2 cells to remember the current maximum and previous maximum, and 2 cells for current maximum, because I can delete the previous one, right? So giving me more number of passes is helpful. Yeah, well,
So how does this differ from calculating the space complexity? So effectively, we are computing the space complexity kind of the thing. How much space is required, right?
yes.
And
So
wherein the multiple passes are allowed.
yes, yes. So that's a good point. In space complexity, you can allow multiple passes. That's right, well. So I can, like, the my head pointer can move back and forth as much as you want in, say, Turing machine models. Okay. And additionally, there are RAM versions of streaming algorithms also. That is that I sample points from the data stream. That's what we'll see in question C and D. But I don't know whether we'll even reach D or not. But that's what I can sample points directly from the list. Okay. Randomly. So that is a RAM model. Okay. And also, Goel, in space complexity, you are looking at very low level details. That is, you even consider like how many bits are required to represent these numbers also, right? You consider log n, right, usually. But that is not an issue when you do algorithms, data structures and stuff, right? You assume that these are constant in terms of representation.
That is not the big difference, because here also what is happening that even though we say that we cannot see, more than one element at a time, we are storing, we are storing everything in the limited space, but then we are allowing multiple pass. So how is that possible that one data is coming at a time and still the data is stored somewhere so that the multiple passes are allowed? Multiple passes, I can predict that three is appearing 142 times only if this data is being stored somewhere.
Yes, yes, of course, there is a data. There is space. You are given some memory. I'm not saying you are given zero memory. The catch is limited memory, not zero memory.
But still, at least I would be requiring of the order of n amount of the space to store everything. Even if the everything is taking
For which
constant amount.
problem?
For like this problem only, wherein you find that the sum of the elements is so we need to find the sum of the n elements, like.
No, you don't need, right? I mean, some of the elements you can do it in one pass only. And
So, but then,
you just need one counter, no?
yes, but then even for the one pass, at least I should know that which all elements are there in the list. And for that thing, I need to store these elements somewhere, isn't it?
You need to store these elements somewhere. Oh, okay. The domain you mean?
Yes.
Yeah.
Somewhere.
Let's assume that you already know the domain. There are models where you study that the domain you don't know, but let's assume that you already know. Exactly. Don't. So what I would say is, don't compare it with the Turing machine model, because the Turing machine model is very rigorous, very rigorous. You need to say, as you said, you need to know what are the elements, because you're thinking in a Turing machine way, right? Well,
Yes.
but those things are out of the window when you talk about algorithms. Okay, algorithms people don't care about those things. I agree that the formalities are expected in the Turing machine model, but there are models which study that. Okay, what if you don't know the domain? Okay,
Mhm.
so that is also considered, but you can assume that you have full. Let's say you have a ROM. Okay, you have a read only memory. You can assume that there is only read only memory containing domain. So you know exactly what the elements of the domain are. Okay, and right.
Yes, yes, yes.
Okay,
I,
so you
I
can assume
understand.
that, because then other kind of complications come up when you bring in Turing machines, because now you can say like, oh, what is the time complexity of moving across the stream? These things are not computed. Okay,
Yes, yes,
and the model that does this is all powerful. Okay, any, by the way, in Turing machine, any computation that you do should also be in that memory. No, let's say log n space is given to you, you should do it in log n space. No, even the computation. Here you can use infinite number of resources. It's just that your memory that you store it in every time you move, is only restricted. You get it?
yes, yes, yes.
Okay. Yeah, Kishore.
Just to add a point to Goel's question. So what I understand from Goel's question was what Goel was asking was, if the data stream has n elements, so the space it should have is order of n. That's what Goel's question was. What my if I am correct.
Um,
If less than order of n space, it doesn't. What do you say? The system or the algorithm doesn't run fully. That's what the question by Goel. What I get.
so from what I understood, Goel was saying that if this is your domain, 1, 2, 3 till n, your algorithm needs to know that, either know that these elements exist already in the domain, but if it does know that it exists in the domain, okay, but I'll be confusing others, because this is, by the way, this is not how to see it, okay, everyone. Okay, so if the algorithm already knows the domain, okay, of the elements in the domain, then it should store these elements in somewhere also. That's what Goel is saying. It should store these
Right.
elements because it needs to recognize that these elements exist in the domain.
That means order of n space is required,
Uh,
not less than order of n.
yes,
Right.
yes.
So
Order of
so
n. Okay,
exactly. Yeah.
but
So
that's, yeah.
this is right what Goel was saying, but
No,
based on my
no, 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 no,
observation
no, no,
and
no.
then
Kishore, this is wrong. Okay, streaming model does not say that this
yeah, yeah,
we
yeah.
don't care
No,
about those
theoretically,
kind of
I mean theoretically, let us suppose it should have order of n space,
uh,
but there are in real time scenarios there will be where we make applications. See, let us suppose we need a application runs once and then it outputs a 10 elements.
yeah.
So what we should have is 10 element space so that it can store 10 elements altogether. But sometimes, based on that itself, the application will be built and then infrastructured. So sometimes there will be some mission critical applications
Hmm,
where the minimum input,
hmm,
output it should store is two elements.
hmm.
Of course, even if it
Yes.
stores two elements, the critical mission will run, and then it what do you say? It won't shut down totally.
Hmm, hmm,
So
hmm,
that's where, due to some reasons, maybe network bandwidth or due to some other
hmm, hmm, hmm,
disastrous events,
hmm,
probably the network bandwidth may lose and the space may get lessened. So
hmm,
that time, probably the data streaming algorithm, what it does is, maybe it will be the range of that algorithm or the application would be from 0 log n to or 0 n
hmm, hmm,
o of n.
hmm,
So
hmm,
within this range, it can it can survive. The application still runs.
hmm. Okay, okay. So, okay, fine. But what I would say is, think of it as, RAM versus ROM, permanent memory and, you know,
Right.
primary memory and secondary memory. That, the fact that, these elements exist. Okay, what are the valid elements basically? Right? What are the valid elements? This is stored in a read-only memory. Okay, the read-only memory contains the domain, while the stream is not up to you, right? The stream is coming one by one. So that is how I would interpret this if you compare it with, say, that model, Turing machine model. But see, the motivation, like you said, I mean, Kishore, like, for example, uh, an idea would be, say, let's say you have all the users of Facebook, okay, and right, and what you want to do is you want to compute the average number of friends. Compute average number of friends, okay, in Facebook, or I mean Instagram, if you want to be, yeah, more relevant now. But if you do this, you can't load this is stored in like so many databases, in some, so many, distributed servers, no. So many, I mean, this I we can't, I don't know, maybe like 10 to the power 10 terabytes or something like, or petabytes or something like that. That's huge. You can't load this into memory, no. You can't load it into your RAM. Cannot load into RAM. Right. How do you compute the average then? You can't load it, the entire thing in RAM. This is where streaming algorithms actually has an edge. You can go one by one, no? You can see each of them one by one. This, assume, think of it like a stream of the data. Okay, think of them as stream of data, and you have very little memory compared to the entire Facebook, right? So this is like n1 friends of the first person, n2 friends of the second person, n3 friends of the third person, and so on. Okay, and then I keep updating, and I have a very little amount of space compared to the entirety of Facebook, and I compute the average number of friends. Is that clear, Kishore? Right. So this is a scenario where it can be useful, and of course it's incredibly useful. But again, like, you can ask, like, going across each person in Facebook, okay, uh, number of friends, okay, going across each person in Facebook, okay, it will still take a lot of time. No, you can't afford to do that. Then what would be another way to do it? You can consider sampling. So that is what streaming with sampling is about. You consider it to be a data stream, and then you can sample values at it at random and talk about the entire thing. Okay. So, but, oh, okay, right. So, okay, but sometimes order log n is called order 1, so this is used a bit interchangeably. Okay, depends, order 1 in the RAM model and streaming model, only standard streaming model, it's order log n. Okay, it's too late to actually talk about all this, but uh, can you give a one pass order 1 space algorithm to compute the sum of the stream? Given data coming, these are natural numbers, okay, from 1 to m.
So, like,
Yes, I can see.
say if the value of a1 is 5,
Yeah.
so then I would be requiring, say, 3 number of the bits to store this value 5. 5 is a counter.
Yes.
And then say the second value is 7. So the value has become 12. Again, I would be requiring, say, the log n number of the bits to store this value 12.
Okay. Yes.
So in this way, I keep on adding the things, and still the log n, space would be sufficient to compute the sum of the string.
Right. Okay, why is this not getting copied? I don't know. Okay, yes. Yeah, okay. So basically, yeah, right. Well, so the basic idea is that you have 1, 2, 4, 3, 2, 7 coming in the stream, right? I have my memory. I have 1 here. When I see 2, I do 1 plus 2, which is nothing but 3. Now in my memory, I see 4, then I'll do 3 plus 4, which is equal to 7. Every time I'm using just one box. Okay, now, what is the size of the box, right? So each of these are order 1 bits. Okay, so I'm summing up order 1 bits plus order 1 bits. How many times? Well, n times basically, but n times. So any value that I get is at most n. So to represent it in binary, order log n bits is enough. Okay, but sometimes it's called constants only because sometimes RAM model they take it as a, it depends on which model. So if you get a question, then please check whether it's a RAM model or a standard streaming model. Okay, now it's over 8 already, so I won't do the other questions. Okay, so just look at this uh, part. Give one pass order 1 space algorithm to compute average of the stream. That time, okay, order 1 or order log n standard to compute the average of the stream.
So that is same as this solution. Say the first value is 5.
Yes.
And so I store 5, and the second value is say 7. So since 7 is a second value, so therefore I add the previous value into it and divide it by the this thing too.
Yes.
And similarly, say the third value is 9. So then I will only be storing sum, and since it's the third value, so I divide this everything by the 3. In that sense,
not by 3.
But then even if I require the previous record also, which has been divided by 2 kind of a thing, but still for this entire calculation, I won't be requiring more than log n amount of the space. The mechanism will be slightly different.
The space I agree, but the computation is incorrect. You said 1 by 1 divided by 2 plus 3 and so on. No, oh wait. So in the beginning, what you said was you'll do 1. Okay, average is 1 itself. Next time you'll do now the sum is 3. You've seen 2 elements, so you do divide by 2. What did you say?
No. So that was slightly incorrect. Yes. So my point here is that initially if I read 5, so it's okay. Then I read 7, so it's okay. And then so I keep on don't do any division. We will do the division at the end. But then we need to keep the count somewhere that how many elements have been read. Yes. Like say, so when I read the first element as 5, so in fact I would be storing this value as 5, 1. When I read the next value as 7, so then I would be reading 5 plus 7, 12, but then 12, 2, that I have read 2 elements in that sense.
Oh, okay. Now I get it. You can do it slightly more efficiently. Okay, what Goel is saying is you again run the sum algorithm, and at the end you also keep a counter, but the count is also known to you. Okay, but yeah, okay, sure. If the count is not known to you, yeah, then you can do sum by count. At the end, this is the average. What if count is not known to you? Well, so count is known to you. Let's say.
Oh, if the count is known to me, then this every time I need not to store this count variable, and I just take the sum only, and eventually when I reach to the end, then I divide it by the value count because that is known to me.
But what I can do is, so see, what I need is average is 1 plus 2 plus 4 plus 3 plus 2 plus 7, no? Divided by 6. This is equivalent to 1 by 6 plus 2 by 6 plus 4 by 6 plus 3 by 6 plus 2 by 6 plus 7 by 6. So every time I divide, yeah, Shogun, that's fine. That's totally fine. Yes, no problem. Okay. So yeah.
Thank you, sir.
Yeah. Okay. Thank you, Shogun. Okay. Good luck. So I do 1 by 6. So I see the first guy, I do 1 by 6. Next time, to this guy, I add 2 by 6. And to the sum, I add 4 by 6. And I keep doing this. Finally, I mean, how much space do I need? This will give you order 1 space. Right? This since you are keeping the count also, it will take log n space.
So my point here is that storing real value may require more space than this log n stuff.
No. That's the thing. That's the assumption of the streaming model. Again, it's you might find it weird, but every element is order 1 space. That's what they assume.
Oh, I see. Only.
Okay. Oh, okay. Now, yeah, Kishore.
You just maybe a silly. I might be asking.
No, it's
See,
okay.
order of 1 and order of login. So when we relate it, is it order of login will be greater than order of 1?
Oh, yes. Order of login is definitely asymptotically larger than order. Okay. Yes.
And order of n log n would be
Larger than log n.
is larger than, okay.
Yes, larger than log n, also larger than n also. Right?
See, these orders, right? Can we just for our clear understanding, can we put into in calculation mode?
Calculation.
How can we do that? How can we do that?
Oh, so for example, log n. Okay, let's compare order 1 versus order log n. Okay. So this is some constant is some, say 7 versus say 3 log n. These are the constants, let's say. So 7 is 7 only. When
so how it is 3 log n?
So
okay,
I'm just assuming the constant. This is just for example. Order means there's a constant term sitting with it, no?
Right.
So when n equals 1, this becomes 7 versus 3 log 1, which is equal to log 1 is it something power something?
Just a log calculation.
Right. This should be 0.
Base 1 log. Yeah, base 2
2
log.
to the power 0 is 1. Yeah. So when n is 2, this is still 7 versus 3 log 2, which is 1. So when n is 3, this is 7 versus 3 log 2, 3, which is something like 1 point, let's say 3 or something. And when it is 4, 7 versus 3 log 2, 4, which is 2. Right? 2 square. So already when n is 8, you keep doing this. This is still 7. This is 3 log 2, 8, which is 2 times 3, 6. And this is times 3, right? And 3 times.
This is n log n, right? What you are doing?
No, this is not n log n. This is c log n, which is order log n.
Okay. See.
N log n grows it's much more rapid.
So the n value should be multiplied again.
Yes, n value multiplies. So already, like if you compare with, let's say, versus n log n, it grows very rapidly. Versus when n is 1, it is 1 times log n, which is 0 again. But versus n is 2, it is 2 times log
4 it becomes.
Is
2 only.
Right?
2.
Now versus this is okay, we didn't put a constant term also, but still it's fine. 3 times log 3, which is 1.3 or something like that, which is something like 4 point something.
Yeah.
But you keep doing this, and you do when n is 8, then n log n is, you see, right? 8 times log 8. 3 is a 24. So if you look at the graph, n looks like this, right? And this is n. This is log n looks like this, and what were you looking at? N log n, right?
Yes,
N
log
log
n.
n, I would expect it to look something like this.
Okay.
Okay. And constant looks like this. Okay. Okay. So I've taken a lot of your time. I hope that's clear. Sadly I could not complete the other two. Please look at these questions. Try these questions. Or you can mail me also. I'll drop in my email also. You can mail me if you say suppose want the solution of these questions. Okay, you can mail me here if you want the solution or feedback on these questions. Please try them. If you are writing the exam, then good luck. Okay, and this was the final problem solving session. This yeah this time's problem solving, yeah, thank you, Goel. This time's problem solving session was a bit uh, I think difficult, but I hope you uh, I mean, despite struggling through it, I hope it was worth it. Okay, yeah, thank you, Kishore, thank you, Ankita, thank you. Yeah, and yeah this yeah in case you yeah, thank you, Ankita, thank you. Hmm. So this will be the final course also. I won't be doing any further courses. Yeah, like I told Goel last sem, I told Kishore and Goel that I that one was my last time, but this time is clear. This time it's pakka my last course. Okay.
Yeah. So this is your final year, or like just
Yeah,
still yet to go?
this is my final. I have one more semester remaining, but
Okay.
this is some extra work that I needed to do because my previous fellowship, okay, PMRF fellowship was ending around March time, so I need to do a few more hours. I needed to do a few more hours. That's why.
Okay. Okay.
Okay.
That's good. So it was it's a very informative interaction with you. It's been like I think 3 courses we have been with you.
Yeah,
So I think
that's
this
it.
third one, even myself and Goyal. So it
Uh,
was very informative, and then even some thoughtful. Maybe it may. I'm not sure whether all this information, whenever it comes to my usefulness,
yes.
I'm not sure, but certainly it comes.
Yeah,
It
you
may be
never.
a random.
Right.
So
Right.
okay.
Right.
So thanks for all the information, and then the so all those silly questions we asked.
Oh,
Okay,
no,
so
no, no.
you patiently attended us. Okay,
No,
and
no, no.
all the best, Bhavya. Good luck for you
Yeah,
too.
thank you so much. Thank you so much, Kishore. All the best to you too. Okay. Yeah, yeah.
Thank
I
you
hope
so much.
part two will become useful. Yeah,
So
in my
what I feel is probably because we don't have a chance further to be in touch. So probably we will be out of this session. Maybe we will be in touch with by our what do you say, social media, or
yes.
some other LinkedIn profiles. We may
Yeah, yeah,
be
sure,
in
sure,
touch.
sure. You can hit me up on LinkedIn. I'll also try to stay in touch in LinkedIn.
So it's
Yeah.
what I mean to say is it's all of them, all of us probably. Maybe
Oh, yeah,
in
yeah,
future,
yeah.
yeah,
Yeah.
that may be very useful for us and or even everyone.
Oh, yes, yes, yes. Actually, yeah, yeah, yeah. That
Thank you
is.
so much for making so much effort. And after attending your sessions, it is very easy to understand lectures. Actually, yeah, the process, the right process is the reverse one. That attend your sessions first and then see the lectures, and the lectures would be pretty easy. And this time you made so much effort. I mean, tremendous effort, and I learned a lot in your sessions. Thank you so very much. Thanks, Ita.
Yeah, 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 yeah. Thank you so much, Goel. Yeah, yeah. I mean, there won't be any further problem solving sessions where we might interact too. But yeah, it was yeah, it was fun with you guys. You asked questions, made the class interactive. So I really appreciate you guys also. It was a great experience for myself also, frankly. So I will miss this. Okay. Yeah. Thanks, Kishore. And yeah, that really played good role, because there will be instances where you teach online and a lot of people don't miss the interaction, miss the sessions. Okay, they'll be like, okay, when will I, sometimes students don't attend and they'll be like, when will this get over? Okay, but that didn't happen to me. I always look forward to doing these sessions because you guys are very interactive. Okay, and I have my share of fun. I learned a lot also. Okay, and yeah, Goel, you are in the academia, so you have so many students, and probably, I mean, you'll have a lot to teach them also, regarding all these courses you do on NPTEL. I really appreciate the effort on your side also, right? That you are taking the time out of your busy schedule, and yeah, the others also, Kishore, Ankita, you too, and that sitting every week for 2 hours continuously and listening to one person talk is not easy. Okay, me personally, it will be very difficult for me also to do that, sit and just listen to someone ranting over the screen. But you guys did it, you sat through it. I'm very grateful, for my part also. Yeah, yeah, having said that, yeah, good luck with your lives. Yeah, Kishore.
Yeah, thank you very much, Bhavya. Probably, hopefully, looking for some time where time permits us to meet again. I'm not
Yes.
sure how, but time knows.
Yeah, definitely look forward to that. Yeah.
Thank you so much. Bye. Good night.
Yeah, okay.
Thank you.
Thank you,
Thank you very
thank you,
much.
Kishore.
Bye bye.
Okay, thank you. Okay,
Bye, everyone.
bye. Okay.